Yesterday we left off with derivatives saying it's usually not difficult to know when you have to take the derivative, actually. It's not a big decision. You'll see some flag words. Yesterday the flag words were instantaneous rate of change, and the other flag word that came up was marginals in economics. And today we'll learn about some new flag words that maybe you've already seen before. Physics. Okay, no word I can think of in education causes more polarity, no joke meant, no science joke there, out there than physics. Some people are like, oh yes, physics. And other people are like, I hate physics. Maybe you've even taken a physics course and you've decided you hate physics. I got to tell you that once you have calculus in your corner, the whole physics game changes. So if you've given up on physics, just hang around for a little bit while longer before you make that final judgment. Because with calculus in your corner, physics becomes a whole new ball game. Yeah? So today, higher order derivatives, whatever that means, and from there, velocity and acceleration. Which actually, by the end of the lesson, I'm hoping to prove that higher order derivatives means acceleration. That's what I'm really going to explain today. The second derivative. The second derivative of a function is simply the derivative of the derivative. Sometimes we'll take the derivative and then we'll do it again. And my job today is to say, why in the world would we do that? Acceleration is the answer. Example. Determine the second derivative of this function. Okay, here I go. Good practice. If you're a little behind, here's me practicing on a, well, actually I'm not going to give it away what kind of function it is. I'm looking for some help here. When you see this thing, f at x equals x over 1 plus x, which of the rules come to mind? Right now, I think we only have 3 rules. We've got power rule, which was to bring down the exponent and reduce by 1. We've got product rule and we've got quotient rule. Which one comes to mind when you see this? It's good to identify it before you even start, so you know what you're dealing with here. Josiah. This is a quotient rule. You can see because it's something divided by something. So then you got to get your mind in that frame. Now, if you haven't memorized it, well, do the homework. I think by the end of the homework, you'll have it memorized. You won't have to worry about, do I have to memorize this thing? So here I go. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. If that's complete nonsense, you're like, oh, I can't even follow what he just did there. Okay, hey, Thanksgiving's coming. Give thanks for 3 days off to do math, and give thanks for not having to go to family dinners, and give hugs to your aunts and so on. You can focus on math. What better Thanksgiving is there than that? How did I do? Derivative of the top times the bottom minus the root of the bottom times top. All over the bottom squared. And this bottom squared thing, again, I'll say again, is really nothing to worry about. It just sits there. In virtually every question I can think of. I don't know another situation where you don't just leave the bottom like it is and you don't even worry about it. What is it about the top that tells me I got to do more work, though? Simon? The minus. The minus is the hint that this isn't nicely factored. And so I'm going to have to do some work. And the work is just expanding and collecting like terms. So I get 1 plus x minus x over 1 plus x squared. And my final simplification here gives 1 over 1 plus x squared. But that's not the end of this question because it asks for the second derivative. So it asks me to do the derivative again. No explanation of why we would want to do that yet. Just like, okay, let me see what happens when I take the second derivative. And what happens often in derivatives, not always, but what happens often is you actually end up with sometimes a similar function in some ways. Now, if you're really with me, you might look at that and go, that's not simpler. That squared on the bottom is going to cause me a real headache, and I agree with you. But I got one more lesson to teach you where exponents in the outside of brackets, it's really not going to be a problem. Yeah? So we haven't got all the pieces of the puzzle together yet. And so we're working on it. I'm telling you, normally we'll be happy when we see this. Taking the derivative of this will be an easy one because it doesn't have variables in the numerator and the denominator, and we can handle it another way. But for now, we're sort of stuck. And so this is an extra f prime step. I'm going to switch colors and say, okay, I'm going to get f prime ready to take the derivative again. So I'm not taking the derivative here. I'm just going to do a little work with this thing to get it ready. And the work we're going to do is, when we've got a squared on there, for now, we're going to expand out that bracket. So I get 1 plus 2x plus x squared. I've skipped a step there. I haven't shown all the foiling steps there. But 1 times 1, 1 times x, another 1 times x, and then an x squared. And I'm going to switch colors one more time to go, okay, now that thing is ready for me to take the derivative of, because it doesn't have brackets with powers on them, or with exponents on them, which is a weakness of ours right now, is how to deal with that. Now I'm ready to take the second derivative, and the notation's so nice. See, f prime is first derivative. If we want second derivative, we go f double prime. It means we've taken the derivative of something twice in a row. And this is a quotient rule. It can be done other ways soon. But for now, we're sort of stuck with the quotient rule when I got a 1 over some messy polynomial like this. A negative power isn't going to help me yet. Now, if you don't understand those sentences, that doesn't matter. You don't need to. I'm just letting you know, if you're looking at this going, wait a minute, can't we do this, can't we do that? Yeah, we probably can do some other stuff, just not yet. For now, we're stuck with quotient rule. Derivative of the top. So easy, it's hard. What's the derivative of 1? 0. Okay, I heard a couple people say 0. Let's go. Derivative of the bottom times the top. And when you get better at these, when you get a 0 like that, you won't necessarily write the bottom. You're like, oh, what a waste of time. Derivative of the top times the bottom, but the bottom is going to get multiplied by 0. So yeah, I put it there, but you'll get better at leaving those things out. Minus the derivative of the bottom. Times the top. And if me doing those derivatives is so fast, you're like, oh, I can't keep up, I can't keep up, I can't keep up with what he's saying. Okay, your strategy, and I just had this talk with Bella, your strategy is to rewind 2 lessons, watch that video, do that homework, and then come back to this video, and you'll go, oh, I get that now. You know, if it's getting confusing for you, derivative of 2x, how did I get to 2 plus 2x here? Yeah. Don't panic. Just rewind. 2 days. You got Thanksgiving weekend in between here. Just rewind and knock it down. It's even better. Your week off next week is only 4 days. So even if you do have a class next week, you only have 4 days of class. So, you know, there is time to get yourself worked out here. Now it's clever time. If you've drifted off to sleep here, you might want to tune back in for this move. It's a beaut. Where was I? Derivative of the top times the bottom minus derivative of the bottom times the top. Good. All over the bottom squared. I could put square on that, but it's not the best move available. There's a more clever move available. See, if I square this, then I'm going to go back and go, can I factor this? And, you know, I'll go back and factor it, but there's another denominator I can use. Simon. Yeah, go back and get this one. Yeah, so when you do have to expand something out like that, just use your head as you're going to go, yeah, the bottom squared. There's the bottom. Yeah, I expanded it out and made it into a form that was convenient for me to take the derivative. But the denominator is 1 plus x bracket squared, and squaring 1 plus x bracket squared is real easy stuff. And normally at that point I'd say, why is it that I have to multiply out the brackets? But in this particular case, it's not really a big problem because there's that 0 there that's going to take care of that other term. Oh, did you see the computer hitch there? I thought it was going to reset. I don't know what I would have done. I lost it. Negative 2x over 1 plus x to the power of 4. And I'm going to put one more line here, because I can do a little better than that. I can do a little bit better than that. I'll talk about it in a second. After I do what I promised I always do, let's go back and check here. 0 times all that is gone. Negative, okay, it's just a 1 out there, don't care. Negative 2, negative 2x, yeah, 1 plus x to the 4th, I'm really good. Everything's wonderful. What's the slightly better thing I can do to this thing to just improve the situations ever so little? Will? Yeah, when you're common factoring, it'll work best. You don't have to, but it'll work best if the x has got the negative, take the negative with you. You'll get a better looking bracket when you do that. And so I get 2 plus x in there. And isn't that good looking? We're not done with this stuff yet, folks. We're going to want to go, okay, when is the derivative equal to 0? when x is negative 2. When does the derivative not exist? Negative 1. I mean, it's going to be easy to read off of these things. Will? Oh, 1 plus x. Yeah. Look at this. Negative 2, negative 2x, and oh, there's more. Look at 1 plus x cancels with the 1 plus x in the bottom. And it happens all the time in the derivative where these cancellations pop out. Yeah, so watch out for them. So I'm going to go to another color. Only because I'm like, oh, this is getting good now. Look at this final derivative. And this is what I was saying is that sometimes when you take double derivatives, you end up with things that are looking simpler. And you're like, it doesn't look simpler to me. You got a cube on there now. Stick with me. We're not done. Within a couple of days, or a few lessons, I'll be able to deal exponents on the outside. We're not going to worry about them. It's not going to be a problem. We'll be able to handle exponents on the outside. No problem. So we got more skills coming yet. Any questions about that? More time? More time? Back to the PowerPoint. The second derivative of the function is simply the derivative of the derivative. We just saw that. You take the derivative once, you take the derivative again. Common notation, you saw the y prime, or f double prime, sorry, y double prime or f double prime. You saw those? This is what it looks like in Leibniz. And don't get freaked out by Leibniz just yet. You'll know the day when I'm like, okay, let's talk Leibniz. For now, it's just dipping our toe in the water of Leibniz a little bit, going, oh, that's weird. And what this means is take the derivative twice of y, and what the variable you should see every time is x. So like if the variable had been t, you would have seen d2y by dt squared. Or if it was height and time for physics people, it would have been d2h by dt squared. You know, so it's just a way of really describing what's going on. Y prime, the primes are used when it's like it's obvious what's going to happen. And this was the question I just did. Primes were fine because it's like it's obvious what's going to happen here. The derivative, those are x's. There's nothing weird about the situation. But situations are going to get weird, and that's where Leibniz will kick in. Okay? And we'll get to Leibniz as we go along. What is the second derivative good for? Similar to the first derivative, the second derivative is useful for solving problems involving rates of change, especially those that deal with motion. See, I think when I typed all this up, I was still so colored by my physics experience. And I was such a physics person that I believed everything was physics. Later on, I've realized that no, biochem, business, all these things, all these double derivative things apply just as much in those. And we're going to get to what double derivative really means. But I feel the need to get sidetracked about double derivative just for a second to inspire you that double derivatives matter. You see, we just talked about COVID and flattening the curve. And flattening the curve's all about the double derivative. Yeah, the cases are still going up, but if they're flattening out, things are going well. And that's what the double derivative talks about is, yes, we're still going up. The single derivative still positive. Number of cases still going up. But if it's flattening, we are making some kind of progress. We like it when it does this, and we'd like to go this way. For sure we would. But if we've got at least leveling out, that's good. And that's exactly what the double derivative addresses. Is this thing flattening out for us? Okay? More on that later in the application sections. But just to give you a taste of why the double derivative matters. We'll play it as a PowerPoint. Problems involving motion. Suppose an object's displacement from a fixed point is described by the function s at t. So this tells you how far along you're moving. That is, s at t tells you how far from a certain point you are. And you get to choose the point in these questions, and you physics people know all about this. You get to choose what's positive, what's negative, what's zero in a particular question. If that seems weird to you, it is possible for me to define my day from here and say, okay, that way is positive, this way is negative, and this is going to be the zero. But that's probably not what I would do. Probably my bed is zero to me. That's where I start. That's my zero, and everything goes left, right, up, down from there. But for you, it's probably your bed. So it really just depends where you're starting, what's a convenient spot to start this whole thing from. So if s is your displacement, that is, it's where you are, s prime is your velocity, which is the rate of change. And you did a little bit of this back in grade 9 and probably in grade 10 science, where you said, oh, okay, how much it's going up by is the speed. Well, for us, that's very simple. It's the derivative. The derivative tells you how much you're changing by. And we often use v at t to denote velocity. So we've got two different choices. When I'm doing problems, I'll use both to get you used to them, is that if you want to talk about velocity, you can write s prime, but you can also write v. Both of those work. What does s double prime mean? Now we're talking about how much the velocity is changing, and what's the word for how much your velocity is changing? Acceleration. Now I don't want to get all physicsy on you, but acceleration is what you feel in the car. You don't feel velocity. Have you ever had that unreal feeling where you're sitting at an intersection, stopped, and the car beside you moves, and you're like, "Wah!" and you're freaked out because you don't think you're moving? Happens to me, my foot will be on the brake, and a car will do this, and all of a sudden it's like I'm confused, I feel like I'm moving. Or it happens when two trains are in the station. Have you ever been in a train in Toronto, and you're on one train, and the other train's moving, and for a second you're like, am I moving, or are they moving? And you can't really tell. Sometimes you can tell because the train, you don't feel the chug, chug, chug like that. What you're feeling is the acceleration. Just imagine we go out in space, and we don't have any planets around, and it's just me and you, and you're coming towards me. We see me and Veronica are coming towards each other in space. There's no way to know whether it's her that's moving or whether it's I that's moving. In fact, it gets worse than that. Both of us can think we're moving, and that makes perfect sense. Or I can think she's moving, and she can think it's me that's moving, and it all makes sense. That's what Einstein was talking about. Everything's relative. It depends on where you are and what you're doing. So, acceleration, though, is what you feel. When your velocity changes, everybody knows it. You know it in the car when someone accelerates the car because you go like this, and then when they hit the brakes, you go like this. You know, that's acceleration. That's your velocity changing. You're just cruising along the road. Cruising along the highway at 120 kilometers an hour feels like nothing, right? You're just sitting there going, reading your book, playing your phone, 120 kilometers an hour. But if you go from 120 down to 50 in a couple of seconds, you feel it. Acceleration is the thing you feel when you're driving. And acceleration is the rate of change of velocity. We often use a at t, but we could also use s double prime. We could also use v prime. There's lots of different notations. I'll use them all to get you used to every single one. What would the motion of the object affect the signs of s at t, v at t, and a at t? Well, it really depends. There's lots to talk about here. S at t being positive means you're bigger than you started the day at. There's a problem looming. I hope you can see the problem looming, is that how do you talk about positive and negative when I start in bed and then go down the street and go this way and come like that? So a lot of the problems will restrict you to one dimension. You just go, you're moving in one dimension. For now, let's just talk about, hey, if I'm going this way, you know, and here's 0, okay? There's 0, and we'll say positive's that way, and negative's that way. And you see, that's very arbitrary. I could have put the 0 over there, I could have put the 0 down there, and I could have put the 0 at Tim Hortons. So 0 doesn't really matter. If I walk over here, these are positive s values. If I walk back over here, these are negative s values. Now, velocity, a little bit different. Positive velocity means I'm going this way. See, but I can have negative s values, but positive v values. I'm moving positively, but I'm in the negative. Or I can move positively while I'm in the positive over here. It's going to get confusing really fast to try and keep track of which is positive, which is negative. Same is true for negative. I can be moving negative velocity, but be in the positive section. And then I can be negative velocity in the negative section, because negative means go this way. Oh, then it gets crazy. You put acceleration in here. Okay, here goes positive, positive, positive. Positive displacement, positive velocity, and positive acceleration. I don't have much room to do this, all right? So here goes positive acceleration. Yeah, see, I'm moving positive, and I'm accelerating positively. I can move positive and accelerate negative. Here it comes. I'm in the positive section. Here it comes. You got to let me get going first. Don't catch me on the first step here, but you can start off fast and then slow down. See, positive velocity, negative acceleration. Yeah, and if you're getting a headache already, that means you're with me. That means it's going good. You should be like, uh-oh, this is going to be a big problem. Yeah, huge. And that's why physics is so difficult. But it does come. Eventually you just come, okay, yeah, got it. One more, over here. In the negatives, negative velocity, but positive, watch this, positive acceleration. I'm going to do it right. I'm going to think carefully. This is going to be negative location, negative velocity, but positive acceleration. You ready? That was positive acceleration. But I was slowing down. How can positive acceleration slow you down? Oh, good. Now you've stopped. Good. I can see a whole bunch of brains going, ah! If I'm going in the negative direction and I do positive velocity or positive acceleration, that would slow me down. Yeah? So positive acceleration doesn't mean go faster. It only means go faster if you're going in the positive direction. Okay. I don't expect at that moment for you to be like, oh, I get all that. What I was trying to do is take your brain and go like this morning and go, or you go, I'm going to have to spend some time thinking about this. I got some examples to help you think about all these things. Analyzing motion. Here's the example you've done all the way since grade 10, I believe. There's an object flying through the air, or flying up in the air and coming back down. These graphs mess people up because they're used two different ways, and I got to talk about something. This is the graph of me taking a piece of chalk and throwing it up in the air and having it fall back down. You're like, no, it's not. It's the graph of a ball flying through the air like this. No, this is time and height. You can do this with x and y and have a ball fly through the air, and that's a different example. The analysis is very similar, but this particular one has time along there. So it's just saying, okay, time-wise, this thing went up to a highest height, and then it came back down again and ended up lower than when it started. So really what I should have done was throw this up in the air. Okay, here it comes. Watch out, Selena. This lesson's in 3D. Okay. This is the picture of what's going on here. Up, down, and ended up down at 0. Okay? So this is a one-dimensional example, actually, with a 2D graph describing it. Let's talk about what's on the screen then. So if physics is not your thing and you're already like, oh, you're messing me up, you're going to want to write an extra thing on here saying, this is just an object going up and then straight down. 1D motion, not left, right, anything like that, just straight up and straight down. We'll get to left, right, for you physics people. In vectors, we'll get to left, right, we'll get to 3D. Like, we'll go everywhere. But we're going to need some help first, yeah? We're going to need to cover the basics first. The initial height is h at 0. How do you find the initial height? You put 0 into the height equation. Pretty straightforward so far. That's the initial. For the initial velocity, you'd go h prime at 0. You'd plug 0 into the velocity equation, which is h prime. And the initial acceleration, you put 0 into the double derivative. Why do I do all that? I want you to know that when it says initial, you want times 0. That's what you're after. Times 0 into whatever equation you got. The max at the top there, we know the derivative is 0. I talked about this the other day. It's conceptually a sort of a difficult thing. The idea that at the top, this chalk brush stops. Did you see it stop? No, it doesn't look like it stops. Now, part of the problem was I spun it that time. I want to really try and throw it flat. Okay, pretty good. And it stops at the top. It's hard to fathom that. And the problem with fathoming it is not that you can't see it stop. It's that it's hard to comprehend what a moment is. Like a moment is like if you pause time for a moment. And there's a moment when this thing stops up there where in the next moment, instead of going up, it's going to be going down. It goes from positive velocity to negative velocity. And the only way it can do that is to at some point have 0 velocity. If you want to go from positive to negative, you've got to hit 0. So at the top, the derivative is going to be 0. This is going to make our max-min question so easy. You know, all that stuff, completing the square, in grade 9 and 10, graphing it. No. We'll just take the derivative and set it to 0. Thank you very much. Power for algebra with easy work to do. And when it hits the ground, this is when the height actually is 0. Not the time is 0, where the height is 0. And this causes the grade 10s and 11s all sorts of problems because they don't know where to put the 0. See, it's 0 everywhere, which is friendly. Makes for good mathematics. 0 is a nice number to work with. But you got to know where to put the 0. And this diagram helps a little bit to understand where you put the zeros. In here, h prime will be greater than 0. We'll have positive velocity on the way up. And here, h prime will be less than 0 as we're on our way down. at all times, all of that stuff you've sort of seen before in other courses. I'm just using h prime to describe it. This might be new for you non-physics people. At all times, the double derivative is negative. At all times, the double derivative is negative. You're always accelerating towards the Earth. Here's how you know. Here's how you know. After I let this go, we call it free fall. After I throw this into the air and let it go, it's now going to accelerate negatively the whole time. Here's how I know. On the way up, as it goes to the top, it's going positive velocity, but that positive velocity is getting smaller all the time. That's negative acceleration. It means the Earth is pulling down on this thing. And then going the other way, it's going faster and faster and faster, negative acceleration the whole time. It's negative acceleration always. It's making it less positive, or it's making it more negative, depending on where it is. See some nods there on that one. Yeah, so that one, after that whole positive, negative, scary stuff there, you might be like, okay, I get it. If you're going up, negative acceleration is going to slow you down. If you're going down, negative acceleration is going to speed you up. Uh-oh. Is this supposed to be perfect yet? No, it probably can't be. If it was that easy, if you've never really talked about all this physics stuff before, and I just explained it and you went, I totally get it all, then everybody would take physics. You know, it's a little bit of trouble. You got to map your way through this stuff a little bit. Oh, examples. Well, here we go. Here's where we try and nail down the details a little bit. Some of these are shockingly easy, and some of them are incredibly hard all at once. I'm going to see if this is going to work. This pen's sort of driving me nuts here. We'll do the quick 5-point calibration here and try and get this pen working a little better. Okay, here's the equation they gave us. And this equation is awesome. This is the perfect equation. When you throw things up in the air and they fall back down, they almost exactly follow this equation. Negative 4.9 t squared plus 12t plus 15. I'm going to give the whole thing away right now. This number comes from the fact that we're on the Earth. That number will change based on what planet you're on or how far up in the mountains you go. It is possible to slightly change this number if you get far enough away from the center of the Earth. Top of the mountains, slightly different number. For our purposes, though, we'll ignore all that and say on the Earth, this number is going to be negative 4.9. If you're expecting a slightly different number, oh, it's coming. It's in there. Don't worry. Watch. This is the initial velocity. No way to know that right now, okay? That's going to come out of all this, but I want to tell you why this is so good. You want to change this equation for throwing something different in the air. You just change this number based on how fast you're moving, and this is the initial height. It's all right there. It's the perfect equation for things in motion. For most motion, this will completely cover it. It doesn't count air resistance, so it's not perfect. It won't perfectly calculate things because air resistance comes in. Is there enough air resistance in my chalk brush to worry about to affect this equation? Absolutely not. There's not much air resistance on something like this. But other things that do face a lot of air resistance that are going high velocity, we need more. This equation gets modified later. Anyways, that's not our problem. We have an easy problem ahead of us. It says determine the instantaneous velocity at 1 second and 2 seconds. And I'm going to break my rule about writing equal signs on one line right here. I believe you should only have one equal sign per line, but this time, in the interest of awesome teaching, I really need two equal signs. If I want to find the velocity equation, what I want is h prime. I want the h prime equation. If you're a physics person, strap in for this next moment. Derivative of the height equation is just what we talked about. It's actually a very, compared to all this product and quotient rule stuff you've been doing, this is pretty straightforward derivatives here. 2 times negative 4.9 there it is. It was there the whole time. You non-physics people are like, what are you talking about? Listen, negative 9.8 is in the physics people's nightmares. You know, like everything is negative 9.8. On the Earth, the acceleration due to gravity is negative 9.8. If you get released from an airplane at whatever height, your velocity will increase by negative 9.8 meters every second. Air resistance kicks in really fast. We're just going to put air resistance on the shelf. Okay? Okay, negative 9.8t, derivative of 12t plus 12, and the 15 disappears. See, your initial height disappears. How fast you're going isn't affected by how high you started out at after 1 second. If you get dropped from 100 meters and you get dropped from 1,000 meters, after 1 second you'll be going the same velocity. You're like, wait, that's not true. People from 1,000 drop a lot faster. Oh yes, much later they do, as time goes by, because they got more time to fall. That was always my nightmare. That's not the way I want to go. Can you imagine falling far enough that you run out of scream? Yeah? And always in the movies it's always like, ah! Imagine falling from somewhere, it's like, ah! You're out of breath, you've been screaming for so long, still falling. You notice that they give parachutists helmets? Have you noticed that? It's the strangest thing I ever saw. A helmet? Can you imagine? You jump out of an airplane with your helmet on, pull the parachute and it doesn't work, right? Uh-oh, pull the safe chute. Well, that didn't work either. You're like, oh, whew. Got my helmet though. Whoa. Thought for a second I forgot my helmet. Oh boy. All right. That easy. Lots of physics explanation in there to try and help you with all the other stuff. But in the end, to find the velocity, you just take the derivative, and you've got a very simple equation here. They want velocity at 1 second. Oh, okay, that's really tough. V at 1 equal to h prime at 1. So you can write either one. You can write v or you can write h prime. They both mean the exact same thing. V is just more convenient, I suppose. And you just go negative 9.8 times 1 plus 12. And I'm doing it all in one line, because I think it's easier to understand like that when you first see these things. It really should be going down the page like we've always talked about in math form. 2.2 watts. H in meters, velocity in seconds. So we're going 2.2 meters per second. So this, they say what it was? Rock was initially thrown up in the air. It had an initial velocity of 12. It was thrown up, and then after 1 second, it was down to, instead of a speed of 12, it had dropped to a speed of 2.2. It was slowing down as it got fired up. So someone's on a bridge, and they fired a rock straight up in the air. Oh, they also wanted the velocity at 2 seconds, and this is what I was talking about last chapter, which is, can you imagine if you had done the h expansion here, t plus h, gone through with 1 second, and then had to do this again, and you're like, now you want me to do it with 2? You have to do all the t plus h's with 2 again. But now that we're much more advanced than that, we can just go, okay, v at 2, that's equal to h prime at 2, negative 9.8 times 2 plus 12, and I get negative 7.6 meters per second. Let's really try and get better at units this chapter, shall we? I've been completely ignoring it so far, even though it hasn't come up on tests very much. But B. Determine the velocity of the rock when it hits the water. This is the exact same question. It says, okay, find v at 1. I did that. Find v at 2. I did that. And then it says find v at some other time. Here's the problem. I don't know what that time is. I don't know when it hits the water. So I got to go back and rewind a little bit and say, okay, how can I use this equation to find out when it hits the water? Now, the bridge is 15 meters above the water, so we want to know when that height hits the water again. We're after height 0, not time 0. Do you see how time 0 makes no sense here? Not after time 0, I'm after height 0. So what I have to go is 0 equals negative 4.9 t squared plus 12t plus 15. And I'm really worried about this very easy grade 10 academic question, because somewhere along the way we don't explain this just right between 10 and 12. So I'm going to try and explain it just right here. This is a quadratic. In quadratics, we do not isolate. That is not the goal. See, the grade 9s right now. This is a poster I just hung in grade 9 last week. Maybe when you were in grade 9, I hung one similar. Yeah? And I'm teaching them, hey, if you want to solve an equation, I'm adamant. You put x on one side, you put everything on the other. And then in grade 10, we show up and say, no, 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 whoa. That's not how we solve equations. To solve quadratics, we get 0 on one side and all the quadratic on the other. So then we're ready to do the factoring, is what we teach them. They're learning it. They're down there learning it right now. They do factoring and say, okay. They say, okay, if there's a coefficient out here, then you got to do decomp, or you got to do trial and error, or whatever your strategy is, because it's not just add to this and subtract to this. So, and then you see the negative 4.9, you're like, there's no way. You're not going to find two numbers that multiply to negative 4.9, two more numbers that multiply to 15 across multiply to 12. I mean, with decimals, it's impossible to factor with decimals. So there's no way to solve this then if I can't factor it. I mean, it would be nice. It would be nice if there was just like a formula for solving quadratics like this. Wouldn't that be great if there was something that was just a formula for solving quadratics? And then we'd name it something clever so that everybody knew what it did. Not like other things in math that are labeled wrong. We would label it the quadratic formula, and then it would just solve quadratics for us when we were stuck. And I did that dramatic thing because it's happened all the time where people get to this question in calculus and they've forgotten that, oh, I've got the perfect thing here to handle this thing. T equals negative b plus or minus square root b squared minus 4ac over 2a. I vow to you that sometime on the Unit 3 or the Unit 4 test, you will need to use the quadratic formula. I need to check. Not that you know how to use the quadratic formula, but I have to check that for sure. But that you know when to use the quadratic formula when the time comes up. And it's when you have a quadratic equal to 0 that you can't factor. Used to call it in grade 10 the it won't factor formula, because that's what it's really for. It's for the situation where it won't factor. Now listen, some of you have fancy calculators that can reduce a lot of steps here. You want full marks in quadratic formula, you at least got to show me this much. I'm not going to show all the steps here today. If your quadratic formula skills are bad, you need to fix those up on your own or come see me about them. But you need to show me at least this much. Negative 12 plus or minus square root 12 squared minus 4 times 4.9, negative 4.9 times 15, all over 2 times negative 4.9. That'll be enough for me. You sub those things in. I'm going to have faith with you the rest of the way. You're like, I know how to type this in to get your two answers. Let's make sure I wrote it down right. Negative 12 square root of 12 squared minus 4ac all over 2a. Ooh, that square root's got to go over there. Hey, practice on your calculator. If you got it in front of you, try it out right now and make sure you know how to type this thing in. Fraction button. Oh, maybe I should. I know what to do here. Here comes the Casio calculator. Menu 1. Fraction. Oh. Into math mode. Fraction button, finally. Negative 12 plus square root 12 squared minus, whoa, left the square root there, I don't like that, minus 4 bracket negative 4.9 bracket 15 bracket down to the bottom 2 bracket negative 4.9 equals. Do you get negative 0.91? Negative 0.91? This thing hits the water at negative 0.91? How can it hit the water? Oh, we'll get back to that. Then I need this thing, but I need that to be a minus. That's where this calculator is so good. You go up here with your arrows, you arrow over and up. Delete, subtract, equals 3. Did you get 3.36? It hits the water at 3.36. That would be the grade 10 question. For us, it's v at 3.36. I'm going to plug that back into the velocity formula, which is h prime at 3.36. A little bit better form coming here, okay? Now I'm not doing it all in one line here. Where was my v equation? Negative 9.8 times 3.36 plus 12. Negative 20.93. Okay, we got a couple of things we got to talk about here. One is, why does negative velocity make perfect sense as this thing enters the water? Brad, it's going down, yeah? So negative velocity, it's going downwards, right? What happened to this? Well, obviously we can't have negative time, right? But where does it come from in the math? It comes from using a parabola to model a situation that really isn't a whole parabola. I used a parabola to say this is what the motion's doing, but really, back to here, here's a good picture of it. I really only have this much of the parabola, and the math is saying, oh, there's another 0 back here, and I'm like, yeah, okay, I know. We're using a parabola. I know, you're confused. I get it. I only want positive answers. Okay, so that's where I like it. Questions there? Well, that was B? Ooh, am I going to have enough room for C and D here? C, initial velocity of the rock. Oh, V at 0. Now, initial means plug in times 0. So I want H prime at 0, which is 12 meters per second. When I sub that into the V equation, where was the 12 in the initial equation? Right here. The initial velocity is in that equation sitting right there. D, am I going to have enough room? What is the rock's maximum height? How am I going to find maximum height? Myself just a little bit of space. What I need about 3 lines of work here, I think. In grade 10, you would take this, you'd factor off the negative 4.9, you'd add and subtract b over 2 squared. You know, you do that whole complete the square thing, you'd get the final answer. They're down there doing it right now. It's great stuff. They'd puke if they saw what we're about to do. What will we do to find the maximum height? Hint coming. What's true about the velocity at maximum height, Veronica? Velocity 0. So nice. We need v at t equal to 0, and the v equation is very nice. Negative 9.8 t plus 12 equals 0. Negative 9.8 t equals negative 12. And so the t is negative 12 over the negative 9.8. 1.22. You get 1.22? I've been doing 2 decimal places all the way along here. I've been ignoring all that significant digit stuff and everything like that. Separate conversation. Okay? Seconds. So even if the concepts that I went through, I really tried to hammer through the concepts of physics, even if those seemed a little difficult to you, you'll find the math penetrates some of that stuff where it's just like, oh, I know what to do here. And the math, actually, there isn't anything, that's all grade 10 academic algebra there. There isn't anything past grade 10 academic algebra. The only thing new is the derivatives, which the derivatives of motion are pretty straightforward. It's usually nice power rule type stuff. Questions there? Will, question. Oh, what is the maximum height? So, t 1.2 seconds. So now to finish that off, I need h at 1.22 seconds, which I just sub back into my height equation. Negative 4.9 bracket 1.22 squared plus 12 times 1.22 plus 15. Someone else typing it in to make sure we get the match up. I get 22.35. Simon? Yeah, I just put that into the height equation, yeah. I'm not saying these are easy because you got to really think about which equation do I sub what number into. You know, and you got to put some thought into that. And it takes a little experience, and that's why there's lots of homework questions for you to practice on. More time here? Sample 2. The position of an object along a straight line can be modeled by S of t equals 3t cubed minus 40.5 t squared plus 162t. By taking it out of up, down, they've taken gravity out of it, and it doesn't look like the standard physics equation you look up. What you can imagine for in a straight line, you can imagine Mr. Todd walking forward and back at the front of the classroom here in 1 dimensions. I got to tell you, moving to 2 and 3 dimensions is no big deal. You just have an equation for x, an equation for y, an equation for z. It really is not a big leap to jump to 3 dimensions. You just have to do each dimension separately. But for now, we'll just stay in 1 dimension, you know, forward and back along here. Determine the initial position of the object. Okay, some of these are easy. I'm not going to act like they're particularly difficult. S at 0 equals 0. You want the initial position, you just put times 0 into the position function. B, determine the velocity at 2 and 3 seconds. Well, velocity is pretty straightforward too. To get velocity, I need S prime. And so S prime here is 9t squared minus 81t plus 162. You just stop me if I'm going too fast in these derivatives. I'm assuming that these kind of simple derivatives are something that you're at least that far in the homework. Even if you haven't finished product and quotient rule, power rule stuff, pretty straightforward stuff. 9t squared minus 81t plus 162. And they want the velocity at 1 second. Or sorry, at 2 seconds. They want v at 2. Trying to do them in my head today to see if I still got it. I'll punch these in a second to make sure. 36 meters per second. Velocity at 2, 36 minus 162 plus 162. Isn't that convenient? And then velocity at 5. 9 times 5 squared minus 81 times 5 plus 162. Ooh, that might be too much for me to do in my head. Is it? Let's try it. 25, 225 minus negative 180. Negative 18. Who's got their calculator there? See if Mr. Todd's getting old. I'll try it again while you're doing that. 25, 180, 225 minus 405, 287 minus 405. Geez, I think it's minus 18. Is it? All right. When is the object stationary? We need v at t equal to 0. If you want to be stationary, we need velocity to be 0. So I need 9t squared minus 81t plus 162 to be equal to 0. And I got to say it again because it happens every year where someone gets to a question like this and they start isolating, they start moving these things over, right? So I want to go through the whole philosophy again. When it was linear, 1x to solve for, it was isolate, x equals number. But with quadratics, the plan is get everything to one side and then see if you can factor it. If you can't factor it, use the quadratic formula. But this one factors, I think. And factoring is much faster than the quadratic formula. So apparently this object stops at 3 and 6 seconds. If you're like, I can't picture everything that's happening here. Don't worry. By the end, I'll get a nice picture of what's happening here, so you can see. But for now, I can still do the math and say, okay, what is the velocity of this thing? Or when is this thing stationary? Which page am I working on here? This one? Go back to here. But any questions? I'm really not trying to rush it. I think that these examples so far are pretty straightforward, and that's why I've sort of accelerated a little bit in how I'm teaching this. When is the object advancing or retreating? Okay, well, if you've drifted off to sleep, or if you're like, these are so easy, you might want to come back for this one, because this has got a little torque to it. We want to know when the velocity, when this thing is retreating or advancing. And so what we're really looking for is when the velocity is positive or when it's negative. You're like, well, how am I supposed to know in a broad category when things are positive and negative velocity? And I really need to explain this carefully, because we didn't get to do rational functions together where we did a lot of this work, and me really hammer home why these tables are so important. But a table is the perfect thing to show off everything that's happening here. That is, there's different sections of the velocity here. If I go to make a velocity table here, I want to talk about the velocity between 0 and 3. And I want to talk about the velocity between 3 and 6. And I want to talk about the velocity after 6. Why those categories? How did I choose the 3 and the 6? Yeah, oh, he said it better than I was going to say it. He says that's when there's going to be a sign change. And I'll just change one word there and say that's when there's a potential sign change, because we've got zeros there. You want to know when this thing's going forward and back, you better start with where it stops. And then look at this. Okay, I really got to talk about this. This is powerful mathematics here. You just take the factored version of this, and this is why the factored was so good, and that's going to get the highlighter. Have I used the highlighter yet today? No, I don't think I have. First time. What a great move. And it's not great because it solves this question in a neat, tidy way. It's great because there's all sorts of situations where if you just think about the factors, you can figure out the positive, negative part of this pretty easily. Do you recall this from the COVID break a little bit, building these tables? Okay, I'm seeing some so-sos here. So let me just explain the whole thing. I've set this up using the zeros of velocity. This is a velocity chart, is what we're talking about here. I took the equation for velocity, I found its zeros, and now I'm going to use that to find out whether, in this section, whether it's going to be positive or negative. You could take a number between 0 and 3 and just sub it into velocity and get whether it's positive or negative. That'll take a little bit of time, but you can do better. You can say, okay, if I choose a number between 0 and 3, and I'm going to choose 1.5 between 0 and 3, and say, okay, if I subbed in 1.5, what would happen here? 9 would be positive, 1.5 minus 6 would be negative, and 1.5 minus 3 would be negative. If I take a positive and multiply it with a negative, and multiply it with another negative, I get positive in that section. Now that you see those positive negatives and the big positive, it might ring a bell a little more from my teaching in advanced functions, where you go, oh, yeah. But if you're lost, let me slow it down for the next round. I want to know whether velocity is going to be positive or negative between 3 and 6. So I pick a representative number. It's going to either be always positive or always negative. I'm going to choose 4. But you can choose anything between 3 and 6. And then I'm going to look at the different factors and see whether they're positive or negative. Well, the number 9 is always positive. When I sub 4 in for t, I get negative when I do 4 minus 6, and I get positive when I do 4 minus 3. If I multiply a positive with a negative with another positive, I get negative in that section. And again, you can just sub the number in. But boy, that's a lot of work, all that subbing in here, because you can get shockingly fast at these tables. Like, as fast as you can write, you can make these tables out once you see what has to happen. In fact, let me do one a little faster, if you're right with me, to see how fast this can go. Number bigger than 6, say 7. Positive, positive, positive. It's positive. You see? It just, whoop, once you know what you're looking for in those tables. Imagine trying to sub with that. You'd be like, okay, so 9 bracket 7 squared minus, no, this is way, way faster. What does it mean? This is when it's advancing. because it's moving forward there. This is when it's retreating. And then this is when it's advancing again. Because I found out when when it's positive velocity, when it's negative velocity, when it's positive velocity. Getting us ready for the hardest question of the day. It says determine the total distance traveled during the first 8 seconds. Let me explain why this is such a big problem. Say I'm wearing a pedometer. I am on my iPhone. And I'm trying to measure the total distance traveled. It counts total distance traveled. Yeah, as I'm walking along, it counts total distance traveled. Do. Perfect. If I use a GPS instead of count total distance traveled, it'll measure where I am from where I started. And it says, okay, you're here. You started your day in bed. You went 8 kilometers. And I look here and it says, you've gone 14 kilometers. Because I didn't go straight from here to there. I went here and there and around and everywhere. You see? The equation's only going to tell you where you started and where you ended. If I put in S at 8, it's going to tell me, oh, you went this far. But it's not going to say everything that happened in between. Let me phrase it another way. Let's say I start at 0. And I walk exactly 5 meters over here. And then I walk exactly 5 meters back. How many meters have I gone? If I went 5 out and 5 back. I went 10, but I'm at 0. See the problem? Important moment then. Here's the important moment. The important moment I want to know is, when did you stop and change direction? Because that's when I got to change all my adding and subtracting. I got to right then, like, stop everything and go, okay, okay, I've gone 5 meters. Stop, think, put that on the board. You went 5 meters. Now you're going to go backwards for a while? Okay, if you're going backwards, I got to count differently and add another 5 meters. Let me build a table to show you what I'm talking about. This table is going to be displacement. It's going to be time and S at that time. And I'm going to choose some very important numbers here. And if you're not sure how I choose the numbers, I hope by the end of the question you go, now I know how you chose the numbers. In this table, I'm going to put the time 0. I'm going to put the time 3. I'm going to put the time 6. I'm going to put the time 8. Don't freak out how I chose them. By the end of the question, if I've explained it just right, you'll go, oh, I know how you chose those now. You're not clever. You just needed to know what the heck was going on. And what I'm going to do is I'm going to find out where this object was at all these times. So, S at 0 is 0. S at 3 is, ooh, that's harder. 3 times 3 cubed minus 40.5, 3 squared plus 162 times 3. Maybe somebody can type that in while I type in the next one. S at 6. 3 times 6 cubed minus 40.5 times 6 squared plus 162 times 6. And then the last one, S at 8. Was the 8 the right choice? Yes, it is. Don't freak out about this. It's like, Mr. Todd's just picking random numbers? No. At the end, you'll go, oh, that's how you knew what numbers. Okay, 3 times 8 cubed minus 40.5 times 8 squared plus 162 times 8. And I need all these numbers. Oh, I can't do it in my head. Does anyone type in them in? Anyone have any of these for me? I'll start at the bottom, just in case you're starting at the top. Oh boy. Getting lots of fun emails, folks. I got 240 for the last one. I'd love confirmation from that, just in case I typed in something wrong. 3 times 6 cubed minus 40.5 times 6 squared plus 162 times 6. I get 162. 3 times 3 cubed minus 40.5 times 3 squared plus 162 times 3. Oh, I totally typed that in wrong. Okay, try again. 3 times 3 cubed minus 40.5 times 3 squared plus 162 times 3. Got it, 202.5. All good? Oh, Emmett's all over it. Okay, now we're ready to talk about everything that's going on here. Let's just walk through exactly what happened. At 0 time, I was at 0. Then I walked out a distance of 20.25 meters. 202.5, thank you. It was all right except I wrote except the decimal place. I was going to say, that doesn't look right with what we discovered. Okay, start again. I started at 0. I walked out to 202.5 meters. Then I went back to 162 meters. Then I went out to 240 meters, even farther. Okay? Now the million-dollar question. How did I get the numbers 0, 3, 6, and 8? Some of those numbers are easier to choose than others. Let's go back to here. How did I get 0 and 8? They go together. Yeah, they said find the total distance between 0 and 8. 0 and 8 had to be on the table. Where did I get 3 and 6 from? Well, that's when it stopped. Those are the times when I'm like, oh, now we might change direction. It's a potential change of direction. I say potential. You're going to find out later. Just because you stop doesn't mean you change direction. It is possible to go out, stop, wave at a friend, and keep going in that direction. But we'll get to all that later. So, what's the total distance traveled? Well, from here to here, I traveled 202.5 meters. From here to here, I traveled 39.5 meters. I didn't travel 40 meters. I traveled 39.5. And from here to here, I traveled 78 meters. See, I got to get all those gaps there. There. Go, tell me, Will. 40.5. Thank you. You're like, yeah, but some of them are positive and some are negative. Not total distance traveled. Yeah? If I go 10 meters this way and then 10 meters that way, I get credit for 20 meters. I moved 20 meters. So total distance. $321. Permission to do the last example and move your break back a little bit? Then I won't teach till 12:25. I'll teach at 12:25 and then we'll see where we're at. We'll see if Sal yells at me if I try and teach again. So I was like, wait, I just asked a question, man. You know what, I'm using Sal only because I feel like if Sal says, hey, you got to ease up, that's a good sign that I should really ease up, you know? Like, because Sal's going to really hammer on this homework, I believe. As are most of you. I'm not... Yeah. Oh, this won't take long. It's actually the same equation from the previous one. Oh, sorry, yes. Sonia tried to trip me there. No, I'm just kidding. It's because of my old man Skechers shoes. They catch on everything on the way by. I was pretty happy with these shoes. I thought those are sort of comfortable and fashionable at the same time. I said, until Max said to me, hey, Dad, put on your old man Skechers. We got to go. I'm like, what? What just happened here? I thought I was cool. You know, with the math and the Rubik's Cubes and the curling. I thought, you know what? Doing pretty good here. I got a note from a student today thanking me for being their teacher and everything like that. I think it's a World Teachers Day and they had an activity in the class. And the last line is, why are you so in love with Tommy Hilfiger? I need to explain that. I don't care what Tommy Hilfiger one way or another at all, actually. I'm just lazy. I don't want to have to look around. I don't have to go shopping. So I'm like Inspector Gadget. I just go to the same store, buy the same stuff all the time because it's just easier. I don't have to think about it. In the morning, same thing. I don't got to think about it. I just pick out a shirt. There's no fashion involved. It's just laziness. Oh, we good here, Simon? Yeah. Simon says go to the next slide. Not funny. All right. Here we go. Easier question. Determine the acceleration. Okay, first find the velocity. 9t squared minus 81t plus 162. We had that in the previous example because it's the same equation from the previous example. You want to find the acceleration? You just take the derivative of velocity. 18t minus 81. You want the acceleration at a certain time? You just put the time in. 18 times 6 minus 81. I get 27. Ooh, let's talk about the units for a second. And make sure I did all that, because I've made some mental mistakes today, so let's do better. 18t minus 81. Plug in 6, 108 minus 81, 27. The unit, though, is completely mysterious. It's meters per second every second. How many meters per second are you changing every second? So it's like meters per second per second. And you see it written like that sometimes, meters per second per second. But most people use meters per second squared. Question. No, you knew that you knew the unit. Yeah, okay. Thought I made a mistake there. Then it says determine when the velocity is decreasing. If I want to know when the velocity is decreasing, I need to know something about the acceleration. So what I really want to know is when is the acceleration positive and when is the acceleration negative? So B. When is A equal to 0? I want to know when do I get acceleration 0? 18t equals 81. T equals 81 over 18. I'm going to squeeze that in there. 4.5 seconds is when the acceleration is 0. Why does that matter? Because now I can build a velocity chart. And say, okay. Oops. Sorry, an acceleration chart. I got distracted for a second there. And then I almost pressed the page reset button. Oh, that would have been a disaster. Acceleration chart. Now, sometimes you get something that's not quite so easy to do the positive negative thing is. I could do with this. I could change this to 18 bracket t minus 4.5. So sometimes you can force the situation and get the factored form, but you don't have to. You could totally just look at 18t minus 81 and go, okay, I'm going to plug in 2. I get 36. I get negative there. I'm going to plug in 5 here. I get a positive there. And so this is where I get negative and positive velocity. So this is and just to throw out for you physics people, you might be like, oh, no, you got to check to see if the numbers are actually getting bigger. Like if your acceleration is positive but your velocity is negative, maybe your speed's slowing down, and that's the important word there for you physics people, is speed. This asked about velocity. This is when the velocity is increasing. I don't know what the speed's doing. It really depends on the positives and negatives. I'm not going to get sidetracked by that yet today, though. Oh, I did B and C right there. The chart gave me both the answers to B and C. It just told me when acceleration was positive and when acceleration was negative, and that tells me when the velocity is increasing and decreasing. When's the velocity not changing? That's when A at t equals 0, which is t equals 4.5 seconds. Those questions are sort of asked in reverse there. To answer the first question, I really needed to answer the second question first. Oh, actually I didn't miss by that much. We'll be done by 10:40.